Okay, good morning. Thank you for waiting, and welcome to the workshop of statistical modeling, statistical methods in global nation dataset mapping. So I'm going to have 3 sessions. First, I'm going to give an introduction of the mapping problem and the data we use, and then you're going to get started. You're going to set up, download everything, and then explore the data. And then we'll focus on the machine learning methods. And I'll separately introduce ensemble tree-based method and convolutional neural network-based method. And after each of them, you get an exercise. And for the ensemble tree-based method, it's going to be in R. And for deep convolutional neural network, I'm going to share Jupyter notebook through Kaggle that I already introduced in the morning. It runs a Docker at its back, so you just need to run the scripts I shared without installing anything locally. And last, we'll look at the modeling process in practice, so how we implement everything and do the bootstrap cross-validation and mapping. So let's get started. So the national dataset mapping is a spatial temporal regression problem that goes from point-based station measurements to a continuous spatial temporal field where for every location, we give an estimation. And because the ground stations, they are located in different areas of the country. So here you can see some of them are in rural areas like these red dots, and some of them in near traffic or industry like these blue and green dots. We can go beyond doing interpolation purely based on distance. So that comes to the line use regression model. It got its name because in the beginning, the variables we used are mostly land use variables like traffic, road density, population, and so on. And now it's evolving, so we are now using more and more data, but the name still kept. And it originally is on a linear regression model. And actually, it's still the most widely used model for prediction and analyzing the sources of the air pollution. But there are also lots of developments, so trying to make better predictions. So that includes integrating spatial temporal dependency, like Kriging-based methods, and general data models, so that tries to relax from the variable distributions, and also machine learning based methods and hierarchical based methods, which are also my focus. So geospatial, so as I mentioned in the morning, that the data is a major driver to our global mapping, so that makes our global mapping so promising. So the predictors we use from road and industry areas is extracted from OpenStreetMap, which is becoming more and more comprehensive every month or year, and especially in European countries. And also we use Earth-Net from satellite imagery and population to represent social demographic data. And we also use wind speed, temperature, and solar radiation from numerical models. So wind speed, it's quite easy to understand that contribute to the dissipating of the air pollutant, and temperature and solar radiation mainly contribute to the chemical reaction process of the chemicals of the species. So here we found it quite interesting. So this is a time series of a city of Australia, the Liverpool, which is quite close to, much closer to equator than Netherlands or many European countries. And you actually found that the lowest air pollutant happens at the noon time or afternoon, but not at night time as we usually expect. This is because the solar radiation greatly shortened the lifespan of the nitrogen dioxide. And also the elevation. So for example, if you are in a village, then the air are very hard to disperse. This is from radar data already with quite high spatial resolution. And we recently also have more elevation product think you shared. So taking the first and second derivatives of the elevation, so we really know if we are at the village or downhill, uphill. So that also can contribute a lot to the prediction. And also, I mentioned in the morning the toponymy measurement, which is a very promising product that was quite new, launched in October of 2017. And in 2019, it's going to have an even higher spatial resolution of 5.5 kilometer. So it measures a quite broad wavelength from ultraviolet to short wave near infrared. So not only nitrogen dioxide, but also other gaseous air pollutant like nitrogen oxide, nitrogen oxide, carbon oxide, sulfur dioxide, methane, ozone, and so on. So that can also help with the prediction because of the chemical reactions. So our interest is to find how to best evolve this product. And we also use the surface concentration product from numerical model called Geosciences, chemical transportation model, which gives global simulation but at 10-kilometer resolution, so a bit low. And for the ground station measurements, so the collection of it is actually a big challenge in the beginning. We have to reach out a lot and go through lots of iterations. But a major part is from this OpenAQ. So OpenAQ is an open air quality community, and the data is becoming more and more comprehensive there, especially since the year 2016. And now probably you can even get more data. So since 2017, it also has an R API, so you can query real-time data and also data in the past 3 months. So I have an R script for it. You can already start from so downloading the data, the first hands-on, so to get set up. I think it would be great if you first look at the data and then when I explain the statistical algorithms, it will be easier for you to understand. So have you downloaded the material from this link? You can download the study material from this link. Y'all got tonight? Yeah. Yeah. And I have a description here, and so if you download it, you get a folder. In this R script folder, you see the introduction, and there's GeoHub 2020 R Markdown file, and you can look at data using this file. So you all know R Markdown, right?
Some question. You make some prediction at the daily basis, monthly basis?
And we are, yes, for this workshop is mostly annual based. Yeah. We are currently also doing temporal prediction. Yeah.
Because the observation data set
yeah, they come at hourly days even.
Hourly.
Yeah. So we, yes. But for this workshop, we mainly do spatial analysis. Yes. And actually in our study, we separated day and night time. Yeah. But for this study, I'm just going to use the annual model. Yeah. Should I go through the script and then Yeah, and then you can do some exploration yourself. So, so you can firstly install the packages. Here there's APM tools. So that's a package I made to facilitate the air quality modeling process. So if you go to this GitHub page, you can also see the R scripts and descriptions. So I also have data in this package. So, you know, if you want to download R package from GitHub, you can just use Delve tools and install GitHub, right? And then, so I have data in there, but this data set actually, because you know, we might have a spatial temporal prediction hackathon for the OpenGeoHub summer school. So because it might be slightly related, so I added some noise in there. So it won't affect your learning process, but just to make sure that just the result you get may be a bit different from the real data. So here you can see the description of the variables, and these are the functions in this package. So most of them are trying to streamline the modeling process. So for example, to calculate the variable importance, and also the error matrix, so like R square root mean square error, so different indicators, and some of them for data pre-processing, and this for converting the units. So this package is just made for facilitating the modeling process. And then after you install it, you can use many of the functions in there. So, and then we can load the data from there. So the global annual data is the major data set that we are going to use. And here you can see the predictor variables, and also we have longitude, latitude, and this value mean is the nitrogen dioxide concentration. Here are some statistics. And we also aggregated the different road types. So we have 5 road types extracted from OpenStreetMap, and we think we aggregated the last 3, so tertiary road and local roads, and formed a new group. But you can also try not doing it. Here is to make some maps. So if you run it, it will generate a map of your of the ground measurement. So I don't know if you are following or. So here, so if you go to the folder where you run the scripts, and then so it will give you a map, and then you can see where the stations are and also their values. Okay, and then we can also look at at the box plots. So so here and also the paired correlation. Here also the spatial dependency in terms of the variogram. So you can just go through these scripts and then to the modeling part. I think we are almost there actually. Yeah, is that okay? And then you have I'll give you about 5 minutes to look at the data. And also there are, also there's also in this data visualize folder, you see 2 R markdown files, the OpenAQ for querying OpenAQ data, and the plot RS for visualizing remote sensing images, and also the output from the numerical model simulation.
I'm having trouble flowing this.
Oh.
It's saying that you have a path. And I think because it's see the space or not? Someone else have any thoughts? No, that shouldn't be it because I do have a well, I did clone it, but now you don't do it. Well, actually, it's let's see if I can fix it on my own so you can just ban it for lecture.
Thank you. Sometimes it is slow.
Is there a specific R markdown you recommend we're looking at now, or is it just time for us to check out the entire folder that you saw?
No, that two-side typing file, and there are two sections. The first section is about data exploration, and the second section about model. You can just go through the first section, refer to refer to. So here, so here, these three files, I want you to look at them. Yeah. You can, of course, also look at the description right here to get an overview if you like. Have you managed to install all the packages? Yeah. So we'll start in 5 minutes. We'll go on in 5 minutes.
You mean installing packages just by running the R markdown?
Yeah. Oh, the variogram. Yes, that's a good question. So that's a quick way of examining the spatial correlation, right? So if you, so the x-axis is the distance and the y the semi-variogram. So if there is a strong spatial correlation, then the data that are closer together will have stronger correlation, right? So then you have, so at the shortened distance, so that is, then that means you have lower semi-variance, the higher correlation and lower semi-variance. So that the data at the lower distance, so that means the data pairs that are very close together, they have low values in the semi-variance. And if the data are very far away from each other, that means they have high distance, the long distance, then the semi-variance will be high. So this shows there's some spatial correlation.
We need to take this into account.
Yes, but for our case, actually, so I have them here for different countries. So so here you can type in the country code. So D for Germany, US for United States, and you can also try other countries. And then you examine this variogram to see if there's strong spatial correlation. So for example, like here, the correlation is not so strong because you see lots of ups and downs. Yes, and you can also set, it's also important to set the cutoff. Also, by the way, the distance is in degree. So this one is about 100 kilometers at the nadir. So you can also change this to see the more local and more global correlation. Here, if you don't, if you hear this section, just by doing it globally. And here actually in Germany, you see the spatial correlation is not so high because you have this, not really like this shape. And in China, it's a bit better. It's a bit better. And you can also think about why this is the reason by looking at the station distributions at this map. By looking at this map, you can think about why in some areas there's stronger spatial correlation and sometimes not. Okay, shall we move on? Or are you all good with this part? Yeah.
So, I mean, the introduction markdown, that was the one you wanted. It's done fine.
Okay, you can let it run probably. Then after the next session, probably I'll give you a bit more time to do further explorations. So we are going to talk about machine learning. I don't know how much you know about machine learning. Like you have some experience with it, or okay, yeah. So Okay, so machine learning is a very broad field and it's evolving really fast in the past several years. And so here I found this a very useful link, the machine learning roadmap. So if you click on it, so it gives you, it's a roadmap of connecting many of the most important concepts. It's very comprehensive and gives you what is happening and the resources. So develop it into machine learning problems, process tools, mathematics, and resources. You can also see this full interactive map. You can really, it's really comprehensive. So here, for example, you get the concepts and the process, what is AI, and then you get also lots of codes. So the example codes from the beginner's level and all the way up to advanced and what the CS student even won't learn. So very practical, and also links of the mathematics and machine learning algorithms. So if you want to have a more in-depth of machine learning, the book of it, the books and cloud service, right? Because very soon it's not going to work on your local computer, and the cloud computation maybe is the most practical way to go. And there are also lots of data sets, so it's very easy to get started and try different things. So this, I think if I go down this, also more. I can't, where are they? I can't find it now, but there are also lots of very new things. So what is the newest developments? I wanted to show you this one about Streamlit. So it's Python based, but it's like R Shiny apps, you know, R Shiny apps that helps you to, so your scripts directly becomes your app. So it's super good for data exploration and showing the concepts and tuning different things. It's still in beta version, but I think I tried it, it's really handful. So I encourage you also to have a look maybe after the course. So in this lecture, hopefully I can give you a good understanding of some most classical and popular algorithms and strategies and the tips we use in the mapping problem. So the machine learning, the history I already found is quite fascinating. It goes back at least to 1940, when it's Walter Pitts and his colleague raised the idea of neural network. And then in 1950, there's a very important paper from Alan Turing introducing the Turing test. So it's actually to determine how computer process human intelligence. That's basically you're talking to a machine, but you don't know what you're talking to. And if you can't tell the difference, if you can't distinguish if you're talking to a machine or human, the machine passes the test. And in 1970s, there's an AI winter, actually a neural network winter, where people's interests started to be shifted to support vector machines. So algorithms with more mathematical background, and also at that time gives better predictions. And then in 1990, there's lots of algorithms. The Deep Blue beat human champion chess player, and the IBM Watson beat the game show, beat human, won the game show Jeopardy. So it's still quite fun to watch. And in 1997, the neural network come back with this long short-term memory. The LSTM, which is a neural network which works on one-dimensional data. In 2006, it really started to show its potential. I even got a name, deep learning. And it also attracted lots of statisticians, and they developed it into a branch of applied statistics called statistical learning, where they focus on statistical modeling and uncertainty assessment. So today I'm going to walk you from the basics to the newest development. So we'll start from the decision trees. So it's a graphic model that asks a series of questions. So for example, a person wants to decide what to do, then he may think, if I'm hungry, and if yes, then do I want local food or not? And then based on these decisions, he's going to and based on these answers, he's going to make decisions. And that, it doesn't work so well, sorry. Yeah, I don't know what happened. I just wanted to say it also maps very well to the air pollution model. So if an area with low populations, then probably there's less air pollution, and if there's a place with high population, then probably we want to look at the traffic count. So if everyone's driving a car, and if yes, then maybe the air quality is very bad. But so this kind of tree-based method have many features. So it's non-parametric, so we are not restricted by the variable distribution. And also, and the most important thing is the redundant variables are ignored. So we don't need to worry about redundant variables. So remember, we really have problems with the collinearity in simple linear regression. But if we just drop those variables, we also lose information. So a tree-based method may better integrate more information, and it can also handle missing data easily. So the missing data will just pass to a branch. So for example, if in the population there's lots of missing data, then the algorithm will probably say, okay, then I'm going to look at the next variable and then go on to make a prediction. But we also know that a single tree is going to fall. So it's not going to work because of the model variance. So a new data set may always follow a different pattern. So what we want to do is to leverage from these trees to grow lots of trees and aggregate them to make, to reduce the model variance and make better prediction. So first method is bagging, where we firstly randomly shuffle data and then take a subset of the data to grow trees. And then by aggregating trees, we may reduce the model variance. And if you want to do it this way, we want the trees to be independent from each other. So that's the idea of the random forest, because the more uncorrelated the trees, the more variance we can bring down. So random forest basically says, I'm going to pick the best variable to split the node, not from all the variables, but from a subset of the variables. So in this way, the trees that grows can be more independent. And then the boosting follows a different approach. So the random forest grows trees independently, so it doesn't pay attention to other trees, but the boosting keeps on looking after the areas where the previous trees doesn't do well, and then try to fit a better model there. So here's why the random forest could work. So if you have identically and independent distributed variables, then each of them has variance sigma squared, then aggregating them will bring the variance down to 1 divided by the number of the trees. But if there are correlation between trees, then it's this formula. So this row indicates the correlation between trees. So you can actually see if the row is very big, then this right-hand term is going to disappear. And then we just go back to grow a single tree. So the algorithm is quite simple. We firstly bootstrap a sample from all the training data and then draw m variables from all the variables and then pick the best variable to split the node. And because the random forest has several limitations, because it's not based on hypothesis test, so it turned to select variables with lots of missing value, for example, and it also does not assess uncertainty. So there are many variations of it, like recursive partition trees, or Bayesian-based sampling and variable selection, and quantile random forest, so trying to address these limitations. So the parameters that are not learned by the model but has set before the model are called hyperparameters. And it is, and I developed a Shiny app for you to look at the adjustment of the hyperparameter, how the adjustment of hyperparameters affect the model cross-validation accuracy and also spatial prediction pattern. And actually, it is very important because many studies actually only look at the cross-validation accuracy, but especially later we'll talk about boosting. So you see that with some boosting method, even though with the optimum set of hyperparameters, the spatial predictions can have many artifacts. So the gradient boosting is a bit more complex compared to random forest. I don't know if you know the algorithm of the boosting. Should I go through it? Or? Yeah. Yeah. So, in the first step, initiate with a constant value. So this F0 means the zeroth tree. So this constant value is found by finding the minimum value, by finding the value that minimizes the sum of the loss function between the observation and this value. So if you take half of the squared error as the loss function, you see that this gamma, the value we want to minimize, is actually the mean of all the observations. So that's our zeroth tree. And then from the first to the last tree, we are going to do an iteration. The first step is to find the direction that minimize the cost function the quickest. So that is by finding the gradient of it. So the gradient is by taking the derivative of the loss function with respect to the previous tree. And again, if you take the half of the squared error, then this y total IM is equal to the difference between the observation and the previous tree. So that is why this is called, the y total IM is called pseudo residual. So I for each observation and M for each tree. And once we got this pseudo residual, we can fit an L terminal node tree to it. And that will divide the data into our LM regions. So here, L indicate each terminal node, and M again for each tree. And then we will pass the data there, and again try to find the gamma that update the previous tree to minimize the sum of the loss between the observation and this updated tree. And then once we found this gamma, we multiply it with the learning rate so that decide the static size that we want the cost function to go down, and then use it to update the previous tree. Is this clear? Great. So the learning rate is a very important tuning hyperparameter, which actually you see also in deep learning, and most of the machine learning based method that use this gradient descent method. If the learning rate is very high, then you risk not finding the minimum, the optima for your loss function, and you risk overshooting. And if the learning rate is very low, you usually need lots of iterations for your algorithm to descend, for the cost function to descend to the minimum. And the stochastic gradient.
Sorry.
case of very high learning rate, the model doesn't find the fit, doesn't find any good.
Yes, because the cost function, so we want to minimize the cost function.
So the red one is that.
The yellow one is when the learning rate is very high,
Okay.
and then you can't find the minimum of your cost.
Okay.
So yeah, so that's very bad. And the red is not bad, but the red, it means you might need lots of iterations for it to reach the minimum. It is clear. Okay, then the stochastic gradient boosting takes the same one as random forest. So instead of fitting the tree to all the data, each time it takes a subset of the data to fit the tree. So by doing it this way, the model becomes more general. And so XGBoost takes a step further from the boosting. It is the most popular, at least one of the most popular methods in the past 2-3 years since it won the Kaggle machine learning competition. So the biggest ideas that makes it better than other algorithms is that it's not only penalizing the loss, but also penalizing the model complexity. So this omega term here. So adding a penalty to the cost function is called regularization. So now we are not only minimizing the loss, but minimizing the loss and this penalty term together. And another great feature of XGBoost is that it's scalable directly. So you can just directly apply it and it can make use of all your free threads, or you can specify the number of threads you wanted to use without needing to use other packages or do the parallelization yourself. So the XGBoost actually origins from the distributed machine learning program. So it's started from this distributed learning. So it does regularization in 2 ways. So the first is to regularize the number of leaves. So it doesn't want the tree to grow very big. So this is done by passing a hyperparameter to it and tell the tree to stop growing if it doesn't reach some improvements. And another way is by penalizing large values of leaves. And that's through 2 ways. One is the L1 norm and the other is L2 norm. So L1 norm takes the absolute value of what we want to penalize. L2 norm takes the square of what we want to penalize. And so here I'm showing the L1 norm in linear regression because the cost function is very to visualize this parabola object here. But for our tree-based method, this cost function can be very complex. So so the figure B is to look at figure A from the top. And these are the contour lines. So here we are trying to minimize 2 things. One, the loss function, so indicated by this blue object or contour lines, so that can show how well we can reconstruct our data. And you get the minimum at this dot here. Right there. And the other is the regularization term. So this green thing, which has the minimum at the origin. And the cost function is minimized when these 2 contour lines touch. So at this, where they touch. And because this touch can happen at the axis, this is why the L1 norm can enable feature selection, because in the linear regression, for example, the coefficients can be shrunk to 0. Is this part clear? Or I don't know if you know lasso or ridge regression already. And so the one norm or lasso, because it's in the lasso regression, enables feature selection, and also more robust. So it's more resistant to outliers. It is not hard to understand because the range takes the squares. So it takes the squares to squares. So that means it signifies the outliers if they're outliers. But the range also has some advantage. So it's more stable. That means it's more resistant to small data adjustment. So if you move your data a little, the range will still give a similar model. And it's also computationally more efficient because it's easy to differentiate the square. But now it's very, very easy to differentiate the square term, but not the absolute term. The absolute term takes a few more steps, and it's also not differentiable at 0. So that is to control overfitting when we are growing trees. And the other way of control overfitting is when we are aggregating trees. So remember, in random forest, we just take the average of all the trees, so that basically give all the trees the equal weight. But the trees can be redundant. So having already known about the lasso regression that result in feature selection, can we also use the lasso to aggregate trees? So here, this P indicate the tree, and the alpha, the coefficients for aggregating the trees. So can we here penalize the alpha to shrink it to 0, so that there are less trees, and we may also better control the overfitting. So how does it work? You can see your hands-on still in this GeoHub 2020. The second part, modeling, you see this lasso plus random forest, that's to do the post-processing. And I also have 2 Shiny apps developed for you to see how the adjustment of hyperparameters affect the cross-validation results and the prediction pattern. So one is for random forest and one for XGBoost. For XGBoost, I have published here on this link, so you don't have to run it locally if you don't want to. So if you want to run it locally, it's just these apps in this folder. I think our internet is a bit slow. But basically, you see a set of hyperparameters to adjust, and then this is, for example, with one tree, the spatial prediction. The spatial prediction is one tree, and the other is 100 trees. So you clearly see that with one tree it doesn't really work, and with 100 trees it's starting to become better. But still there's artifacts, so you also may need to adjust the learning rate, for example. Oh yeah, here it comes. So you can adjust these different hyperparameters. Here it gives the cross-validation accuracy and the prediction pattern, which is very important to look at. And then if you adjust the number of trees, this will all change. Okay, so you can go through the scripts now. I'll give you about 20 minutes, and you can ask questions. So basically, these 3 files, like 1 markdown and 2 Shiny apps. Oh yeah, that's a good question. Yeah, it's a gradient, extreme gradient boosting. That's to boost. Yeah, but it's also very difficult to set up. So you really need to tune the hyperparameter as well. But once you
Use
do
gamma,
you do
gamma
yes, in the space I also have a description of all these hyperparameters.
Okay.
Yeah, so you can tune. So if you don't tune them very well, it will give you lots of artifacts. Even though the cross validation accuracy may show an output for running flows, the prediction patterns are not so right.
Okay, because random forest you have also some tuning like on the side and so on.
Yes.
But when you tuning, it doesn't make so much change.
Yes.
Rather, you say it's straight boosting, you really need to well tuning parameter.
Yes. Yes, that's a very good remark. Yeah. Yeah, the random forest is the least sensitive to hyperparameter tuning.
Okay.
And then you go to boosting, it's becoming more and more difficult.
And in terms of yes, cross-correlation, correlation between variable is the reason constraint with state boosting. It's like correlation, autocorrelation.
Oh, no, it's the same.
Yeah, so it's still.
You mean one is more robust?
Yeah.
Oh, that's a very good question. I think the boosting is more robust because it's based on the previous prediction, and it also has this regularization path. So 3 ways of doing the regularization. So I think it's more robust. Yeah. So the key point is really if you don't tune the XG boost well, then you'd rather use running for this.
And there are some particular methods that you suggest for the
I think maybe I will develop my method, I think. Because for now,
you can comment the script in the section where you run state boosting.
I have the R markdown file.
Okay.
It shows you how to tune it. So we do a grade search. We use the R caret package and do a grade search of the hyperparameter. Actually, you will find that the optimum setting when you reach to the lowest cross validation accuracy, your prediction patterns are not so good. Maybe you may still have artifacts with your optimum hyperparameter setting according to your cross validation accuracy. So that's why I developed this apps for you to also look at the prediction pattern. It's okay, I think I got it. So here, the modeling part, you see this hyperparameter optimization, but maybe I suggest you to run it after the workshop because it takes very long because it does many iterations. And then you have this running the models. I think you can start from here. So from regression tree to random forest and this post-processing strategy, which is actually really new. We never saw any studies, but it actually gives better, improved results. So you can also see the number of trees that are dumped after running this lasso random forest. You can see we can reduce the number of trees from 1,000 to like 40 if you run. I think maybe I can also run. Do you prefer to run it yourself or like me to run it here and then? I think it's better you run it yourself. Yeah, and ask questions. So if you can't run it, there's also this results here. So you can also go through it if you have problems in running it. This is the result of the R Markdown file. So if you click on commit, then you generate that HTML file. I think I can show. So here, actually, you can see the coefficients of different trees. We can reduce the number of trees to only 100 if we do this lasso random forest.
You mentioned of group is still used in group with like a class. So sort of more sensible to operate.
Well, it's actually, yes, it is sensitive, but it's also because of the hyperparameter setting. I meant that I still meant that it got artifacts when I got my optimum tuning using the grid search optimization. So I was really trying to motivate people to look at spatial patterns as well. So it's not like the model is not robust to outliers. It's more because of how we tune the hyperparameters. Yeah. And of course, yeah, and another thing is that we need to have probably more data compared to running forests. Yeah. But my experience is it's really a big improvement from random forest if you do it well. If you do it well.
For the model validation, do you use the typical validation parameter or
Oh, you mean the we use the set of matrix. So root mean squared error, mean absolute error, and also relative values. So relative root mean squared error. So you see that if you run this arrow matrix function, so that's in the script. So I put all those indexes in this package I write. Yeah. We are also this ongoing research that we are trying to find better accuracy assessment methods. Yeah, to more really taking care of the spatial prediction patterns. So not only by visualizing it, but also trying to find some ways of quantifying it from a spatial perspective. Yeah, but that's the only place where you have observations. Yeah, but we're also trying to get some indicator that can shows you there's lots of artifacts also. Yeah, for better accuracy assessment. So here, this arrow matrix gives you different indicators. And if you go to the function itself, I have a description. I think I probably have a description somewhere. Yeah, those are. But yeah, what you raised is a very good point. I think there's no any this spatial related cross validation methods, but we are trying to find out. Thank you. Yeah, I'll let you know.
Usually, I mean, mapping the field is something.
Yes.
For somebody like this, localize it instead. So rather than calculate the overall distance forever, and they can new values of then they get all the problems together.
Oh.
And then it calculate the distance square.
Yes, yeah, that's one of them.
Back from the receiver, mapping just the receiver units.
Yes.
There is a big run. So rather than to try to homogenize bigger areas, and then you can see something like more or better.
Yes.
So that one
Yeah.
is kind of partial group instead.
Yeah, that's a good strategy. And we are also trying to do something from the spatial predictions. So the predictions around those points, we are trying to see if it's more consistent.
Do you also value, if you predict a certain value in a certain cell, does it count as a bigger error if the cell is further away from the truth, for instance? Like, do you take distance of into account? The accuracy?
Can you repeat?
Yeah, I'm not quite sure how to phrase the question, but for instance, if you take for instance, trying to predict land use change, and you have a forest and it's like 10 cells, and you predict deforestation in one cell, but it actually it actually happens next to it. That would be a pretty accurate prediction, but it would be less accurate. I mean, it's still an error, right?
Yeah, I think yes.
Would you count that as like a less clear error than if it would be predicted 10 cells westward?
Yeah. Okay. Yeah, I see your point. I think for us, we have less this spatial pattern because our stations are far away from each other. Yeah, but I think maybe I can still consider a point.
Are there ways to do that?
What do you mean?
Something like that.
Think yeah, we can implement. Yeah, I think I can. I don't know any software for doing it, but I think the things we can program and see if it's
All these methods is common for us. Remember that we are working with the table.
yes.
Observation and the predictor. That table doesn't know where are these points.
Yeah.
So all these methods we apply in spatial context, but they are not structured.
Yeah.
Until you do something. So there are only two methods. One, all you insert predictors that give you information about where you are predicting. So you can insert lat long, two predictors. It gives you something, but for example, in other forest, so they predict because you can get style, line, so it's a less 2 degrees, 2 days, 2 degrees, flat line. Okay. Probably you also will get it stick. Or you can also use as a predictor, for example, the density of the point, or buffer. So for example, on the buffer system, right, as a predictor, will give you information of how much comfort. So this is one way that we can everybody can do. But then there are some other methods that I can insert inside the algorithm of the information about the density of the location.
So spatial context.
Spatial context. It's the only one paper on spatial context.
Oh.
But from a Greek line, from a Greek line. But he also developed a library, but it's still in the stage. So I think it is well using the American side. So in that line, also when you start the receiver, you should think a way to address this problem. Because it is so, yeah, one pixel close is more easy to be the forest. So maybe even having the information as a predictor of the nearby pixel is already should go the matrix, your matrix, and then you should everything as one pixel to the left, right, and eight corner, eight position, and maybe even more to the six around it. Then you can give some information by location.
So there is a paper.
There is this spatial random for I think we will do it. But then I see that he has not so many. It's also in a really small journal. Yes, there are. Geographical.
Okay, yes.
For the programmers, yes. But, but I didn't see so much implementation with the collaborate this maybe from that how you
Yeah, thank you. Okay, I got more for validation or for prediction.
for the
For prediction.
in the same way. You can do partial.
Validation. Okay, yeah, thank you. I also learned something. We're actually trying to do also mixed effect random forest. So that's also, so that's for cluster data. So regions within cities, within countries within continents and so on, and to capture the similarities between, within countries and also the patterns between countries. Yeah, but that's not for validation. So I'll look at this paper and see. In the afternoon, I think maybe. So the next one, the convolutional neural network-based method, I think it better takes account into spatial pattern because it's purely like spatial based, convolutional filters. Yeah. So instead of like what we are now doing is to calculate the road density, so the road length in different buffers, right? And instead of doing that, we just go directly from the transportation networks and automatically and apply the deep convolutional neural network there to automatically extract features from there. So not to aggregate data into a point anymore, but to just look at the entire spatial pattern and then scan through all over the data to do the prediction. But still, in terms of validation, it's just always we do point-based. I think that's for probably all the studies now as point-based validation. So I really want to, I've been thinking a lot about a better accuracy assessment methods. I also thought about using this topomy because it gives the global coverage data. The topomy measurement, so the satellite, the Sentinel-5P measurement, it has a coarse resolution, but it has a value 7 kilometer. Yeah. So we are also trying to use that to contribute to the cross validation because you have a value everywhere. But the thing is that measures the column density, so which is not directly related to the surface concentration. So we are interested in the surface concentration. That is, yeah. Yeah, so we want to collaborate with some other teams so they can, yeah, use the numerical model to give surface prediction, and they can use it also for validation. So to, for example, have the predictions matching the pixel of the topomy Sentinel. Yeah. I think we can discuss further about this validation. I'm really interested. Okay, is everything running well with this, Chris?
I have finally gotten everything to.
Okay,
I was starting with the
I still have
whole-
the install package.
Oh,
But you can just keep going. I'm still following.
So anyone else on their package problem? Or can you run the Amazon? Oh, yeah, probably the GEO, the virtual machine, has a lower version point.
3.4.
Okay.
So it's very better.
Yeah, maybe try to upgrade your. Do you have any problem? Oh, it takes a while. Yeah, because the internet is very slow here. So,
Because we're all frantically downloading all kinds of stuff right now.
Yeah, I should have let you to download it already. But yeah, you can also look at this HTML file to get an overview of the output.
Yeah, you have that.
Great.
Like that it fails, that's nice. You can work with that.
Thanks. Do you need any help? You're just waiting for it to use. I don't know the last half hour. Did Tom say we are going to have a discussion or should I go on? Will you all stay for the afternoon session? Okay, then I'll move the deep learning to the afternoon session. Okay, and also modeling in practice. So now you can just run your scripts and then ask questions. You want to? Oh. Oh. I have the example in the script. So after you finish that, pardon? Yes, I wrote the function. And let me show you. Can you see me? Yes. Yes, yes. You see it in the script. So let me see where it is. So this lasso plus random forest, this chunk, this function. And here you can see the cross-validation if you run this function. And there are also two additional things. So in this other folder, I made two scripts just for you to have a better understanding with the machine learning techniques. So one is an ensemble, so to aggregate like random forest, XGBoost, all the different models so to not just ensemble trees, but to ensemble models. This can always improve prediction. The problem is it's slow, of course, because you have to run all the different models. But in this machine learning competitions, you see the winner, they usually resemble different models as well. So I have this small R scripts here for you to see how to resemble models. And there's also one for difference between the statistical models like linear regression and machine learning models. Because, yeah, okay, I'll say it later. Now we're about browse test. So,
if you're working with ensemble models, have you ever looked at the MOR3 pattern?
MLR3, yeah. I looked at that. Yeah. I think 1 year ago it was not maintained, or something,
Yeah,
or
like
2 years
people
ago.
are working on it. Also, some people from the foundation are continuing to.
Yeah,
They're also
I
writing
think.
a book about it. So it seems to be quite in development.
Yeah, they
It might be
started.
interesting to check out if you're working with.
Yeah, I'm aware of that. I think they started a few months ago or a year ago
Yeah.
or something. Yeah. The yeah.
They have a check. Yeah, yeah. You can combine. You can add different laws to a task simultaneously. I mean, I just started checking it out. Mm. Yeah, that's true. Yeah. It is very, very complex.
Super learner, yeah. I think I remember it also a few years ago or something. Yeah, but I don't remember the results now. Yeah. Yeah, could be. Who? Work for who? Oh, yeah. And also the Google had this automated machine learning. You know that, Patrick? Automated machine learning, auto ML or something from Google. I think they do things probably a bit better. Yes. Yeah, probably you can try. I'm actually shifting a bit of my machine learning works to Python because I sometimes feel they have better support or a more rigorous community. Yeah. I feel more people are working in machine learning in Python. So, yeah. Are you all R users? Or you use? Good, that's right.
I'm saying that into art. So working with Python for 1.5 years.
Oh.
So I'm still orienting like what packages to use for the machine learning. That's why I'm quite interested in what you're using, like free package. But I don't know yet, so it's.
Yeah, just to try both and compare. So this ensemble, this R scripts, I also try to ensemble, so myself, so try to optimize the model prediction from different models. You can try if you like. But I think I give you lots of homework probably. Lots of things. And anyone wants to run Python locally? No. Because I also have instructions for installing Python if you don't want to run it online. It's for the afternoon for the deep learning part where I do it in Python. So I'm going to, probably you can already see it. Here is, maybe you can already try this link. I would recommend you to create an account. Then you can also use the GPU and TPUs there. And otherwise you can only stay there for 15 minutes. You can't use GPU or TPU, but it's really the biggest community for machine learning practitioners, so definitely. And it's very easy to have an account, so maybe.
So you can make your account, you can take the data.
Yes. Yeah, share your scripts. So so if you have an account, if you click the edit, you can already run my scripts. So either run everything, or you can just run as our notebook. Here you can have the accelerator. So you can choose GPU. None means CPU, GPU and TPU. The TPU requires a bit configuration, a bit setup, but it's quite easy to do. So it's really very good startup for people who don't have a GPU.
Yeah. I heard about the but I never did.
Find any time to enter competition.
Yeah, only five.
No, also our notebook. Yeah. Let me. I can show you.
So you have software
You can choose to use Jupyter Notebook or just Python shell like thing, or R Markdown. Yeah. So there's 4 things you can. I think if I do new notebook, and then you can choose if you want to do. Yeah. Here's a Python or R. Yeah.
and in the say in the library that you need is that you just install it.
You can install it, but it runs the Docker at its back, so it already has lots of machine learning packages pre-installed. So yeah.
The library on the floor.
Yeah, exactly. So here, for example, you know, it's the same Keras and TensorFlow, and you can just import already. It's same as library in R. And for the things that is not there, you can easily install it using for Python with this pip. So yeah. So I think for teaching and so on, it's really cool. Maybe you can. No.
If you use Google Colab, you can
Oh yeah.
Google Colab is also good.
Yeah, yeah.
The physical part.
I thought so, but yeah, they are a bit similar, but this has GPU and TPU. I don't know if better for deep learning. Yeah, yeah. Okay, then I'll try that. And it also has good connection with Google. So you just can use Google Cloud.
You can also connect your Google Drive to a Google Colab notebook and just pull it back from there.
Oh, so probably they are quite similar.
Yeah.
Okay. So I think maybe you can have a Kaggle account now, and maybe in the afternoon it's a bit easy if you want to. Otherwise, you can stay for 15 minutes or so on my scripts. And also, you can still see my scripts. You can still see my scripts and results and so on. But if you want to run it, it's better to have an account. Did you mention carrot ensemble? Or no, the carrot ensemble. You didn't mention the carrot ensemble. No. Oh, you did. Yeah, it's quite old, and it's actually quite slow.
Yeah.
Yeah, I have the scripts here, but I commented all of it out because it's too slow. But maybe you can try if you want to. And also I have mixed effect model here. Yeah, I think it will be too much if I talk about it. That's also what we are currently doing. So the mixed effect model, as I talked about, is for hierarchical data, right? So to better integrate more spatial information for prediction, because between countries there's disparities and within countries there are similarities. So mixed effect model, there's one development, so to use random forest and mixed effect models. I think that's super interesting. And I have also a Kaggle scripts shared here. So you can also try this out if you are interested in. It actually gives better result than random forest and also, yeah, than random forest. I forgot if it also gives better prediction than XGBoost. But it's I think it's very interesting. So. Yeah, I think it's not in R, or the R1 is no good.